Okay, so with this diagonalization, let's try to put two questions that you can solve. And it could be a question on the exam, right? So here's a nice question on the exam. A equals to 1, 2, 4, 3. A, find the diagonalization of A. Okay, that's number one, and which we already did, right? B, compute A to the n in general. Okay, and C, compute E to the A. Let's try to solve part B and C. We just solved how to diagonalize matrix A. So, well, I said this is diagonalization, but usually for finding A to the n, you really want to, yeah, okay, so for part B, let's start with the following fact, that we have some P inverse AP, which is a diagonal matrix, right? And I'm in need of finding A to some power n. So what do? We take this to the power of n, this to the power of n. And I gave this a name. Do you remember what this was? This thing inside? It's called, I don't remember, conjugate. Okay, conjugate. Yeah. Why is conjugate important? Because if you have, say, this multiplied by itself 3 times, what happens? This can be simplified, right? What happens? They cancel, and you end up with P inverse A cubed of P, right?
Yeah. Yeah.
So if you take general nth power, what happens on the left side?
It'll expand, so it'll become.
If you write this n times, all the p's in between will cancel out, and you're going to end up with what? P inverse
A to the
A to
n.
the
A to the n, P to the n. No, P. You only have P that survives on the far right, P inverse surviving on the far left. They can't cancel because matrices are not commutative. And this is D to the n. And therefore, this will be always true. Once you have a diagonalization, this is always true. You can always write down A and P, A n. You can move this P inverse to the other side as P. P to the other side as P inverse. Okay? Is this okay? Should I show you the intermediate parts? I think you're okay, but let me just show you the intermediate parts. So what I'm doing is I'm multiplying P inverse both sides. I'm doing the same exact thing on here. Okay? I'm treating both sides exactly the same way, right? But I like this because this is going to cancel with this, and this will cancel that one, right? And you end up with just, oh, this is A to the n. You just end up with A to the n equals to P, D, and P inverse. Okay. So that allows you to find out the A to the n in general. Okay, so let's compute this. So answer to B would be A to the n is equal to 1, 1, 2, negative 1 times 5, 0, 0, negative 1 to the nth power times 1, 1, 2, negative 1 inverse. So if I compute this, that's the answer in general. Which means I need to know what 1, 1, 2, negative 1 inverse is equal to, right? So we use the formula for the inverse matrix, which is 1 over 1 times negative 1 minus 2 times 1. You switch these two around, you negate these two, and, oh, what is that? Negative 1 minus 2, negative 1/3. So it's going to be 1/3, 1/3, 2/3, negative 1/3. That's P inverse. Okay? Okay, so we're now almost ready to compute. How do you take the nth power of a diagonal matrix? What do you guys say if you have 5, 0, 0, negative 1 times 5, 0, 0, negative 1? What do you get? 5 squared, 0, 0, negative 1 squared. Right? So if you take the nth power, what's going to happen? This n goes inside. That's the point, right? Why do we like diagonalization? Because for diagonal matrices, you can take nth power really easily. You know what? Let's just write 1, 1, 2, negative 1, and put 1/3 later. Oh, they have to be the same. Okay. All right. So now, see, I just factored the 1/3 outside. All right. So now I do this times this gives you 5 to the nth. This times this gives you negative 1 to the nth. This times this gives you 2 times 5 to the nth. This times this gives you negative 1 to the nth. You still need to multiply by 1, 1, 2, negative 1. And then later you have to divide by 3. This times this now gives you 5 to the nth plus twice of negative 1 to the nth power. And then 5 to the nth times 1 plus negative 1 to the nth power, negative 1. And 2 times 5 to the nth, this times this, so minus 2 times negative 1 to the nth. I'm doing this really fast, so please check my calculation. I might be wrong. This would be 2 times 5 to the n, and plus negative 1 to the nth power. Okay, this one I'll just put as minus. Is that right? This times this. So this I don't need. And this times this. I think I'm right. Is that right? Okay, and you need 1/3 in front. Okay. Yeah. And that's it. Okay. You just have to put 3 inside. That's enough. You have a question?
Is there a reason why you don't cancel out the 2 negatives for the fourth matrix? For the negative 1 to the n?
Oh, these?
I was thinking on the first one.
This one?
Below it.
This one?
Yeah. Can't you just do the multiplication?
This times this.
Mm-hmm.
1 times this.
But then right there, the one when you just did it, the negative times the negative 1 wouldn't it just be positive and then you would do multiple times?
No. It's a negative 1 to the squared, for example, is a negative 1. Right? This negative survives.
God.
Right? Yeah. Okay, so that's a to the nth power. Any questions? All right. Now, what about What about e to the a? Okay, first of all, who remembers what e to the a means? Who remembers what e to the a means? Huh?
Exponential function?
Yeah, but how do you exponentiate a matrix?
You bring the matrix outside.
I don't know what that means. We talked about matrix polynomials, right? If you have a function of x, you can replace x by a, and also constant term by some constant times I. Okay? The same idea. What is e to the x as a polynomial? Is there such a thing? How do you write e to the x as a polynomial?
Oh, the Taylor.
Taylor series. What's the Taylor series of e to the x? 1 plus
1 over x.
Yeah, 1 over 1x, 1 over 2 factorial, x squared, 1 over 3 factorial, x cubed. So, what would this mean? Identity plus 1 over 1, a. Instead of x, you have a, right? 1 over 2 factorial, a squared. 1 over 3 factorial, a cubed. That's what it is, right? Again, this is extremely hard, even with this. Even if we know a to the n, it's extremely hard. So instead of using this, we'll take a slightly different approach. We already know that a can be diagonalized, right? So we know that a is what? It's p d p inverse. That's what a is. We figured that out. Right? Therefore, this is identity 1 over 1 p d p inverse 1 over 2 factorial p d p inverse squared 1 over 3 factorial p d p inverse cubed. So we have that. Now what? Now what do you do? Well, we know what to do with this, right? What happens? What happens with this 3? This is a conjugate, isn't it? Right? If you have a conjugate, what can you do with the exponent outside?
It goes to the d.
Yeah, it goes to d. So now you have, you can even put I as p inverse. 1 over 1 p d p inverse. 1 over 2 factorial p d squared p inverse. 1 over 3 factorial p d cubed p inverse. Do you agree that I is p inverse? Because I commutes with anything, right? Actually, multiplication of I doesn't do anything. So this is same as p times p inverse. So it is same as identity. Or you can just say I commutes, so you commute I with p and p times p inverse cancel, so it's I. So once you do this, now what do you know? This is p times identity plus 1 over 1 d plus 1 over 2 factorial d squared plus 1 over 3 factorial d cubed plus da 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 with p inverse. I can factor the p outside and p inverse outside, okay, both sides. But what is this? This is the exponent of, that's the exponent of d. So we just found out a very important identity, which is if A is equal to P to D P inverse, then E to the A is same thing as P times E to the D P inverse. And moreover, because diagonal elements, taking nth power diagonal elements are so easy, if you have 5, 0, 0, negative 1, and you put it in here, if you think about the nth power, it's really just this to the nth powers and these to the nth powers, and you're adding them, so you end up with e to the 5th power 0, 0, negative 1. E to the negative 1. So in general, this is true. If you have e diagonalized with lambda 1, lambda 2, this is going to be e to the lambda 1, 0, 0, e to the lambda 2. Just like that. Yeah. Diagonalization makes everything very easy. Okay? All right, so now we're almost there. Therefore, our e to the a is going to be same as p is equal to 1, 1, 2, negative 1. And then e to the d is e to the 5th power, 0, 0, e to the negative 1 power. And then the inverse was the same thing with 1/3 multiplied at the end. And we just have to multiply this out, and that's the e to the 8th power. Okay? So that's going to be e to the 5th, e to the negative 1, 2e to the 5th, negative e to the negative 1, times 1, 1, 2, negative 1, times 1/3. So it'll be 1/3 times this would be e to the 5th power plus 2 e to the negative 1. And then e to the 5th power minus e to the negative 1. 2 e to the 5th power minus 2 e to the negative 1. And then 2 e to the 5th power plus e to the negative 1. Now, if this was used for solving differential equations, I told you that the reason that we like this is because it appears when you try to solve system of differential equations, right? So you have e to at. You need this one instead of this. So, but the only difference would be instead of 5, it will be 5t. Instead of negative 1, it will be negative 1t. And that's called a fundamental solution because that can solve a system of equations. So if you had a system of equations such as x prime y prime is equal to 1x plus 2y and 4x plus 3y, if you try to solve this, then any solution will be x, y in general will be the solution that can be written as e to the at times x0, y0. So that's the general solution. But since this is now a differential equations class, I'm just referencing this to justify why we would like this. Of course, I'm not going to be asking you this for the exam, but you still have to know how to do these things. That's why we do diagonalization. Can I stop the video and do the next one?